So welcome back to my third lecture. Today we are moving to discuss some predictability issues. So there are Ensemble behind, and the reason why this study has been based on Ensemble should be clear because of what we said yesterday. But the discussion is more about how far ahead can we predict phenomena. Phenomena with different scales, with different spatial scales, with different temporal scales. So that's the idea of today, to revisit Edward Lorentz butterfly effect 25 years after we have been running operational Ensemble systems, and to try to see whether we have moved forward or not. The key point of this lecture that I want you to take home are two, more or less. There is not a unique definition of a forecast skill limit. It depends on what you try to predict. So what I sometimes will call the FiSH length, F for forecast, S for skill, and H for horizon, forecast, the FiSH length, depends on the field you look at, on the scales, on the temporal and spatial scales. And the second point that I will try to show you is that we are well beyond what was thought to be 2 weeks. But actually, if we look carefully at what Edward Lorentz did and what we have found in this work, we are not actually far away. It's just that in the 60s and 70s, the approach was limited to local and instantaneous fields, while here we are trying to move forward. And why did we move forward to look at different spatial and temporal scales? Because thanks to ensembles, we now know that we can predict certain phenomena for longer. Okay, so this is roughly what I'm going to show you today. So first, context, ensembles why, we'll go through it very quickly, and then I will show you some results on where is this forecast skill horizon. Is it 2 weeks or is it longer? Where is it? And then I want to discuss a bit the physics behind. Why do we get the numbers that I'm going to show you? What's the physical reasoning behind it? And then conclusions. So if we go back to 1969, Lorentz, Lorentz did 2 or 3 very important works in this area, based either on looking at forecast from the European Center, geopotential height at 500, 7-day forecast or 10-day forecast for up to 5 winter seasons, if I remember correctly. He did that type of study. Then he did another type of studies where he was looking at analogs using SNWF analysis. And he was applying some error growth models to try again to see how fast are the trajectories that are close at one point, 2 different atmospheric states diverging. And using this data, he concluded the range of predictability is about 2 weeks, 16.8 days. It's mentioned in one of his forecasts. And then in one of his papers, in one of his other papers, he says, these results offer little hope for those who would extend the 2-week goal to 1 month. So this is where we were. Butterfly effect, forecast error, at one point grows so fast that there's no way we can do prediction beyond 2 weeks. So this is what we know from theory, but actually if you think about the last 10 years of prediction, we know that actually we can do better than that. Okay, we can still predict severe events at some grid points only few days ahead, like this storm that hit the flood in Catania of 2013. So there are phenomena that still are predictable only a few days ahead. Like this one. But there are other phenomena that we know we can predict much longer ahead, like the MJO, which is the most important low-frequency organized convection pattern that propagates in the tropics, or the NAO, the North Atlantic Oscillation. For example, if we look at the MJO, these are results from Frédéric Vittard, published in Ensemble paper last year. We know that today we have a forecast with an AC anomaly correlation coefficient of 0.5 up to almost a month ahead. Where if we look at the 0.6 line, we reach the 0.6 line now at about 4 weeks, 23 days. NAO over Europe. Okay, these results are based on 20 years of forecasts, of ensemble-based forecasts. NAO, we are a bit shorter than that, but so we are about 11 days. We look at 0.6 ACC. If we look at 0.5, we are about 2 weeks. And one of the reasons why now we can predict VNAO more accurately than a few years ago, this is 2011, this is 2000, is because we have improved the prediction of the MJO. And we have seen that there is a link between organized convection in the tropics that triggers Rossby wave propagation that eventually send a predictable signal over to the Euro-Atlantic sector. So there are physical reasoning behind this. If we go even larger scale patterns, we know that we can predict even over Europe extreme weather events like heat waves or cold waves. This is a heat wave that hit Italy in July 2012, I think, yes, where we were able to predict this phenomena. So even for an area like Europe, which is extremely difficult to predict longer, a few weeks ahead, we were able to give a good prediction up to 4 weeks ahead. And if we move to the tropics, we know now that we can predict even larger scale phenomena like El Nino. This is SST prediction in an area in the middle of the Pacific up to a year ahead. What you see here is the range of the old system-free ensemble forecast of 15 members run predicting the El Nino 1 year ahead from the 1st of November 2011. In dotted you see what was observed as SST. This is the forecast 1 year after. From cold to warm, more or less neutral conditions. And this is the latest forecast for last year. So if you think about what Lorentz, okay, and even if we look at Europe, seasons 1, 2, 3 months ahead, there are some phenomena that we can predict months ahead. This is the case of the drought that affected Europe in May, June, July 2012. This is an index, a drought index, as computed using reanalysis, so very close to what was observed. You see this area of very high values, so very dry values, very hot and dry values. This was the forecast from the 1st of February, so a 4 to 6 months forecast. In color, in shading, you see the area where the ensemble PDF was far from a climatological PDF, so where there was a signal, and the signal was for warmer conditions. This is a forecast 1 to 3 months ahead, a much clearer signal. So even over Europe, despite the fact that it's a difficult area to predict, we can predict seasons ahead. So if you think about Lorentz and these results, it looks as if, no, it's not true that there is a limit of 15 days, but the forecast skill horizon depends on what you try to predict. The problem that we had before this work was done is that these measures of skill are based on metrics which are different from what we usually use for instantaneous values. So these are usually based on anomaly correction coefficients computed looking at projections of work onto 2 EOF computed in a certain area. So there is a lot of post-processing behind it to extract the signal. So what we wanted, and it's very difficult to think about how these measures of skill link to the measure of skill we are more used to, like a continuous run probability skill score of forecast over Europe at day 3 from the Ensemble. So what we wanted to do was to look at, to try to apply the same metric to 20 years of forecast, try to look at phenomena with different scales, so go through a gradual spatial and temporal filtering, and look at whether we could find similar results, i.e. that there are phenomena that are predictable for longer time than others, and try to estimate up to which time can we make these predictions. Ensembles Y, you know everything about it because we discussed it yesterday, so I'm not going to discuss it. What I've been using was the Ensemble prediction system. This work took about a year to be done because we had to crunch a lot of Ensemble data. So the period that we considered was July 2012 to July 2013. It's a period during which the Ensemble system didn't change. It had still 62 vertical levels. It was coupled, 51 members at this resolution. So we used the monthly forecasts, which were issued twice a week for the whole year. So we had about 100 plus cases. On top of that, what we wanted to do was to bias correct this forecast as we do when we generate the products, which you can see on our website. Probably monthly forecasts are usually expressed in terms of probabilities of anomalies in the upper tercile, in the lower tercile. Seasonal forecast, the same, probabilities or of anomalies, or so we wanted to do exactly the same. So to correct this forecast, we did exactly what we are doing with the operational system. So we took the reforecast set. So as you know, for example, 13th of March of 2013, we ran a 51-member ensemble. At the same time, we ran 5-member ensembles once a week for the 5 weeks centered on the 13th of March for the past 20 years. These are 500 forecasts. These 500 forecasts, these are 500 32-day forecasts are used to correct and bias correct this 32-day forecast. This is my ensemble, bias corrected ensemble forecast, which I'm going to score and look at. As a reference, we have used a 100-member forecast defined by past analysis. So we took the analysis at this day, we collected all the analysis of the subsequent 32 days. This is one member of this reference climatological forecast. And then the second member will be the analysis from the 6th of March for 32 days and so on. So if you count, these are 100 members. So we have a 51-member ensemble, bias corrected, as a reference, a 100-member climatological ensemble. These are the two ensembles I'm going to use, and what I want to do is assess where is the forecast skill horizon. How do I define the forecast skill horizon? Well, the forecast skill horizon is defined. Okay, let's first of all think about what Lorentz was doing. Lorentz was mainly working with a single forecast. So he would do something like take the error curve of a single forecast, look at a kind of reference value, for example, the average variability of the analysis, and look at when the forecast error was reaching an asymptotic value. Okay, this was based on single forecast. We are going to do it with Ensemble, as I will explain in a minute. What I also want to point out here is that we will do something similar, but we will also take into account the fact that there is some variability around the mean error or the mean score, so that, and we will take that into account by adding a confidence interval. Okay, details, I might skip the detail, but essentially we have done it so that we would take into account the fact that this is the average of 100 skill curves, and this is the average of 100, so we are going to put to take into account the fact that there is variability around this average, and that the variability is larger for longer time step than for shorter. But I mean, you can clearly see what's the idea. This is the skill of a forecast I could build using simple climatology. This is the skill of a forecast based on a dynamically integrated model. If we do this exercise using single ensemble control forecast, this is what we find. This is the score of this reference, the red curve. You see it's moving up and down. Here I'm only showing you the mean score. In the paper that we're just finalizing, we will have all the uncertainty around. This is how the error growth of the ensemble control grow over the 32 days. And you can look at where the two match, and you can immediately see that we are past the 2 weeks value, even by looking at instantaneous local values. So this is taking 500 geopotential height forecast, grid point value by grid point value, look at the whole northern hemisphere, compute the, in this case, the RMS error of that forecast, compute the RMS error of this climatological forecast defined by analysis, compare the two, which is equivalent to what Lorentz did in one of his papers from 1969, where he said 16.8 days. He used only 5 years of ECMWF forecast, winter forecast. We have used 1 year of 32-day forecast, and looking at the same variable. But as I said, we want to think ensemble because that's the right way to do it. So how do I define forecast skill horizon in ensemble? In the ensemble world, where we have to think about probabilities? Well, when we issue an ensemble forecast, first of all, okay, this is, for example, an observed value. I have a very good 5-day ensemble forecast. It's a PDF. Here is normal. My reference ensemble would be probably a wider PDF, PDF that doesn't change with forecast time because it's fixed, it's based on analysis. So this ensemble is far from a climatological distribution. As forecast time evolves, it will tend to spread out and to converge to the climatological distribution, what Anders sometimes called regression towards the mean. So my ensemble, if it's a reliable ensemble, as trust me, we can assume it is over 32 days, the ensemble would eventually collapse into a climatological distribution. When it collapses to that, I don't have any more forecast skill. So this is where I lost any skillful information. So in ensemble mode, assessing where this happened has been done by using as a metric the continuous run probability score, which, as I said yesterday, is an integrated measure of how close is the PDF of the forecast to the PDF, to the observed value. The skill score has been defined by comparing the CRPS of a Bayes-corrected ensemble versus the climatology. We have worked with about 141 cases, so 1 year and a half. But then because there is a seasonal signal that to filter out a seasonal signal, we actually restricted the analysis to only 1 year, so that we don't have more of a season than in other. And these are, okay, the ensemble as I said before. So this is what we're going to look. When does this collapse to a PDF happen? This is the equivalent figure to what I showed you earlier, but built using CRPS. So this is the CRPS of our 32-day ensemble forecast. I'm still looking at instantaneous grid point values over Europe. Again, a detail. When I say instantaneous, I mean forecast day 5 is the field at day 5. Grid point value, I mean fields extracted on a grid which is about 1.5 degree resolution, okay? It's at a truncation T120. Why this truncation? Because we know, based on work done by colleagues, that the actual resolution of our ensemble is not really 30 kilometers, but it's 5 times that. We know that the ensemble has enough energy of a small scale only up to that resolution. So for me, grid point value means I take one grid point every 1.5 degrees. I look at northern hemisphere's geopotential height. This is where they hit. And if you look at where the two crosses, we are past this 16, 17 days. We are around 21 days. And this is for local instantaneous value. So this would be the equivalent of what Lorentz did. We are 1 week behind that. How can we now look at different spatial and temporal scales? Well, the idea is simple. Let's apply some spectral filtering or time averaging. Okay? So we have we've done both things. The first thing is spatially to go from T120 truncation to T60, T15, T7, T3. This is an example of what the impact of spatially filtering the fields on one case. So as you can see, as you go from T120 to T30, T15, T7, you lose the details. The large-scale field remains, but when you go past T15, you may essentially are left only with really the planetary waves. Okay? And doing the effect of spatial filtering has been studied by moving from instantaneous values to 1, 2, 4, 8, and 16-day averages. Again, this is the impact of going from taking the instantaneous values to averaging over 1 day, 2 days, 4 days, 8 days. Okay, so these are the two games that we're playing, and actually we have done the exercise where we would apply both of them in sequence. So we could have very low frequency, large-scale fields or low-frequency instantaneous field or large-scale field. Okay. And this is how the curves of CRPS that I showed you before look like if you apply it to this spatially and temporally filtered field. So first curve is exactly the same as what I showed you before. Climatological ensemble, the instantaneous values cross over about 21 days. If we look at 4-day averages or 8-day averages, you can see that, first of all, the natural variability of the field, the asymptotic value moves down. There is less variability because the scales are smoother. But also the time when the error, say the CRPS, or the time when the forecast PDF collapses to the climatological PDF, moves farther to the right. Now, and if you, you can build this curve. Actually, we have a software that can do the comparison, taking into account also the variability around the mean, and taking we define the forecast skill horizon, the time when there is an overlap of 1% between the two distributions. So we consider the ensemble being skillful only up to the time when 99% of the scores lie to the right, so more skillful than the distribution of the climatological forecast. So this in some way simply confirms what I showed you earlier, but based on using different metrics for different patterns, MJO, NAO, El Nino, but applying exactly the same metric to exactly the same fields to exactly the same ensemble forecast. Okay? So it's easier to think about whether I can trust or not monthly or seasonal forecast. It's also easier to understand, given this 32-day forecast, how can I extract a predictable signal? Well, if I want to predict something 3 weeks ahead, well, I can only do it if I look at large-scale patterns, time average. No point in trying to give 4 weeks forecast of instantaneous grid point values. There is no skill in that scale. But if you look at time averages or large-scale fields, there is. Because we've done the exercise looking at the 2 extratropics, northern and southern hemisphere, and the tropic, in the paper we also make consideration of whether one area is more skillful than the other, and so on. And the results actually change a bit. There is sensitivity, not terrible, but there is some sensitivity, say plus or minus 2, 3 days, 4 days, between the results that you get if you look at different areas, if you look at different variables. This is T850. The main conclusion is the same. As you look at larger scales, the skill horizon moves further to the right. So what then we could do, we did was, okay, let's compute these times when the two distribution collapse for a range of fields, geopotential at 500, T850, wind at 850, wind at 200, temperature at 200, and 3 areas, tropics, extratropics, tropics, northern hemisphere extratropics, southern hemisphere extratropics. So we have about, I think, 14 different variables / areas. And then we put them into this type of graph to see how far ahead we were from this 2 weeks value that was suggested in 69. And if you do that, this is roughly speaking what you find. if you look at instantaneous values, there are some fields over some areas that actually are predictable even up to 30 days ahead. So we are past beyond the 2 weeks time scales, and the more you time average, the longer the values are. Yes?
What is on the x-axis?
It's what I said before, which is, so we have a range of these bars. Each bar represents the time when we hit the forecast scale horizon for a certain variable and a certain area. So I just tried to summarize. No? So this simply says there are some variables over some areas that can be predicted beyond the 32-day, even beyond the 32-day forecast range. So it makes sense also to think about extending the monthly forecast to 45 days, which is something we will do this year. How can we explain what we found thinking about Lorentz 1969, thinking about what we know about error growth from the small scale to the large scale affecting and spoiling even the larger scales? How can we conciliate these two different messages? We know that errors grow, affect the forecast. There are certain scales that we cannot predict, and the fact that there are certain scales that we can predict. And why is now the value beyond 2 weeks? What happened in the past 25, 30 years that we didn't do 30 years ago and we're doing now? Well, there are some major advances that we have done in the simulation of the phenomena, in the complexity of the models that we are using, and in the way we initialize them. Any scales, this is a nice diagram from Brian Hoskin's 2012 paper. Suppose you want to predict a phenomenon with a certain spatial and temporal scales. The evolution of this phenomena is influenced by wider, longer time scales that can maybe force it, can maybe propagate some predictable signal onto them. It's influenced by some external forcing. For example, if there is a very dry summer condition and we are able to initialize the soil, the memory of the soil, it might last for 1, 2, 3 months, and this could induce predictable signal on large-scale patterns over Europe. For example, the drought over Eastern Europe over 2012. But there are also the small scales, some free scales like convection, turbulence, that can actually affect the phenomena and make it less predictable, or some small scales which are slave to the large scales, convection embedded into MJO type of organized convection. So when we talk about predictable forecast scale horizon of 5-day average forecast truncated at T30 or T60, we have to think about the larger scales and the smaller scales and the external forces that can actually influence their scale. And what happens is that this is a representation of what can happen in the atmosphere, is that yes, we have propagation of error growth from the small scales that we cannot simulate, that we are not able to simulate, that we try to simulate with stochastic error schemes. So these are going to gradually make it less predictable, the larger scale. But at the same time, because we are able to initialize the larger scales better than the small scales, why is that? Well, if you think about what I said yesterday, we have observations covering the globe, these observations at certain scales, and they are able to constrain more of the larger scales, for example. So the larger scales can make it, can form some way some smaller scales and keep them predictable. So it's the interaction between error growth from the small scales and the propagation of predictable signals from the large scales that defines where the forecast skill horizon is. Now, if we go back to Lawrence, 1969, the model we were using at the time, okay, it had a very low resolution, probably T100, something, or maybe even T63. But more than the resolution, that model didn't have a dynamical ocean, had a very poor surface representation, didn't have soil, layers in the soil, didn't have a good representation of a stratosphere. So it was missing the phenomena, and very importantly, we didn't have enough observation to initialize it properly. So it was missing phenomena, and it was missing the initialization of a large scales as we do now. So this is why what was thought to be 2 weeks is now 3 weeks. It's the combination of having made the models better, the inclusion of more processes, the fact that we can initialize them, that also helped extending the forecast skill horizon for instantaneous fields. If we think about then the large scales, well, the large scales now, because we have, for example, a dynamical ocean that evolves on with a lower frequency than, for example, the atmosphere, that can also induce skillful prediction of a longer skills. Okay, and this is, for example, how you can draw that box diagram for a prediction of blocking over the Euro-Atlantic sector. Results by Frederick Vittard and others before Cassou clearly showed that MJO, the fact that there is an active MJO in certain phases can actually make it more predictable, make it easier to predict weather over the Euro-Atlantic sector. And the interaction between MJO and El Nino is important. So you need to be able to simulate with the ocean accurately the warming of a SST to predict this interaction well enough. But at the same time, we have also the propagation, the error growth propagation from these scales. And so one thing is the models of today are able to simulate more processing than the models of 30 years ago. The second thing is these processes that were simulated 30 years ago are now simulated better. This is an example of a change, of the impact of a change we included 4 years ago on the statistics of precipitation over the tropics. So this is the statistics of a precipitation of a model before that we were using 5 years ago, which is the same as what was called season system 3, compared to the observation statistics. And this is, the orange is the model that then has been used in the season system 4, so much closer to the observed statistic. We were precipitating too much, too low values, over prediction. So this changes the way, this was changing the way organized convection was organizing, and so we were not able to predict MJO propagation with the model of system 3. When we put in cycle 36 at 2, which is essentially the orange, actually this improved the simulation of convection, improve the simulation of organized convection, improve the simulation of the MJO, and this led to improvements of the prediction of the VNAO. Now this is how the propagation of MJO looked like in the old system. From the day 1 to a day 10, there was a collapse of the intensity of the MJO, while now the MJO remains with the right, so propagates correctly as in the analysis in black, but it also maintains the intensity, while before we were essentially not able to have a strong enough convection in the area. So it's phenomena like that led to the fact that now the NAO prediction is much better, and we are able to simulate the link between NAO and MJO more accurately. Right, so to wrap up what I said, if we go back to 1969, one flap of a seagull's wing would forever change the future course of the weather. Such a change would be realized within about 17 days. Well, these statements were made using analysis from ECWF, which were generated using the model at that time, a model that was low resolution, didn't simulate the same processes today. They were based on looking at the scale of forecast done using that model. The model today is more complex, simulates more accurately the same processes, and simulates more processes that we were not simulating at that time. It starts from initial conditions which are more accurate, especially the large scales are initialized better. The stratosphere is simulated and it is initialized. The ocean is initialized. So the phenomena in the atmosphere that evolve with slowly are better initialized and simulated. And this is what helped moving the forecast scale horizon, even for instantaneous local fields, from 17 days to about 21, 22 days.
Roberto, you must mean Lorentz in 1982.
Maybe. But there is not a big difference between 69 and 82. He did 3 or 4 studies, one using analysis at that time, one using geopotential height fields, one using simple error growth model fitted on analysis. So, and all of them point to the same conclusion, 2 weeks. 2 weeks is, and in fact 2 weeks is what every now and then when you read on the when you read about chaos theory and weather predictability, with the wing of a butterfly can affect the weather after 2 weeks, and then no way to predict for longer. So this is what made it possible now to do forecast beyond 2 weeks, skillful forecast beyond 2 weeks. And this is what made it possible for certain phenomena to be predicted even 4 weeks ahead. Now, the data set that we have been using in this study was based on the ECWF 32-day ensemble. The plan is to repeat it using the seasonal ensemble, because then we can go past the 32-day range and even go past the 8-day time averaging field. And the idea there is also to look at whether we can, where is actually this limit? Because for some of the fields and some of the areas, we found that the limit was past the 32-day. So why did we move to summarize? Well, reduced initial errors, more complete models, coupling to land and ocean, for example, better models, improved mass processes in other area. The use of ensemble method and ensemble techniques is another key advance. All the other difference between what we did and what Lorentz did is that we look at PDF and how when PDF were collapsed into climatological PDF rather than looking at single forecast. Understanding of a source of predictability scale analysis. So in some way we need to move away from the seagulls and think about fish. And this is the end of my talk. Thank you.